So hello everyone, I welcome you in my class. So in today class what we will do, we will move towards the aircraft directional autopilot design and analysis. So we have already done the longitudinal autopilot design and analysis, where we did how to use a elevator and a throttle in an automated manner in order to complete a longitudinal flight, and then we move towards the already completed the lateral autopilot design, where we have seen how to use the aileron in an automated manner in order to control the roll rate, roll angle and course angle. Okay, but in last class we have a little bit given you the hint like what is the importance of roll, because when you take a coordinated turn, then you may skid or slip. So in order to prevent that, rudder is required in order to make a coordinated turn. Okay, for example, like if you are taking a turn, so there will be more lift here and less lift here. So it will, due to the centripetal force, aircraft will take a turn. Okay, since this is a here it is more lift and less lift, so it will try to, aircraft will try to take a yaw also. So in order to prevent this yaw, we have to use a rudder in order to make a perfect circle, where you will, where the side slip angle will be 0 and aircraft will not lose its altitude. Okay, so this condition is known as a coordinated turn flight. And another scenario you can consider, let's say when there is some kind of wind, and if you want to handle that wind, or if you want to kill the side slip angle, like we in coordinated turn flight pilot generally do, okay, or autopilot do. So we need to design a directional autopilot. That means we have to design a rudder deflection in an automated manner that will be able to kill the side slip angle, and that can handle the side slip angle. So the question is, what do you mean by the side slip angle? So already I said that when there is any relative airspeed with a wind, so resultant velocity vector is this direction. So what the angle is making with the resultant velocity vector with a plane of symmetry is known as a side slip angle. Okay, so already we have discussed this. So when you take a component, okay, then what will be this component? V cos beta, right? V cos beta. And what will be the another component? V sin beta. Okay, okay. And when you take this component, that means this is the angle of attack alpha, right? What the angle is making with the x-axis. This, after the resolving, this vector it's making some angle, right, with the x-axis of a physiology reference side. That is the angle of attack. So this component will be cos alpha. Okay, and since one component is cos beta, so another component will be, for example, when you have taken the component, this is a v cos beta, right? So v cos beta, so this along the x-axis is cos alpha, along the z it is sin alpha. So now you can this call as a v small, and this is u and this is w. Okay, so uvw is the velocity vector on the x, y and z direction in a body axis. Okay, so now this we will use later part in this lecture. So now first we need to obtain a, like in this class what we will do, first we will see actuator modeling and all, already we have discussed, same procedure will be applicable to here as well. Now in the directional autopilot design, what we will do, we will take a rudder to side slip angle transfer function. Side slip angle means beta only. Okay, and then we will discuss the beta control loop, control architecture, right? So what is the first step? First step is to write a dynamic equation and then obtain a transfer function. Okay, so we will look for those equation where the side slip angle is sitting. Okay, so already I told you, already I explained you in the aircraft dynamics lecture about the aircraft 6 degree of freedom, where we have seen the y direction equation v dot, right? So that equation we will take. Okay, so what is that equation? V dot equal to minus Ru, okay, plus G cos phi cos theta, okay, and plus half rho v square s, okay, and this is Cy divided by m. This is the equation. Now further we can write V dot equal to W minus Ru plus G cos phi cos theta and half rho v square s by m, and Cy we can expand like this. Cy naught Cy beta into beta and Cyp into Pb divided by 2v and plus Cyr Rb divided by 2v plus Cy delta A into delta A plus Cy delta R into delta R. So this represents the aerodynamic model in a side slip case. This Cy is a side force, and we know that rho is the density, v is the velocity, s is the wing area, m is the aircraft mass, phi is the roll angle, theta is the pitch angle, pitch rate, w is a UVW or the body axis velocity along xyz direction, and r is a yaw rate. Okay, we already discussing these things in a aircraft dynamics lecture. If you want to know more about this aerodynamic model, you can go back to the my aircraft design course and you can have a feel for it. Okay, now so what are the dominant uh, derivative when you consider this sideward motion? Obviously Cy beta into beta. Cy beta is more dominant one, and also there is a yaw rate, right? Cy beta and Cy delta will be the dominant one. Okay, see, when you deflect the run, there will be sideward motion, right? So these are the coupling derivative, Cy delta A. Okay, and what is will be the next step? You should change this V in terms of cos beta. So already we did, right? Here, see, V equal to V sin beta, right? So if you differentiate, what will be this? V cos beta into beta dot. Okay, so if I am designing the controller to kill the small side slip angle, that means side slip angle is not too large, so that means beta will be, cos beta will be close to 1 if beta is small. So I can write V beta dot small v. Okay, this I can write. Okay, beta is small. Okay, so now if you substitute this in this, what you will get? I will substitute here, right? I can substitute here V beta dot. Okay, V beta dot. Okay, so now I can write, see, I want to kill the side slip angle, right, using rudder. So I have to write the equation in terms of beta dot, right, in terms of beta. Okay, so this you can write 1 by V W minus Ru plus G cos phi cos theta. This you can write. Okay, and what other things you can write? See, what is the strong derivative is there, you keep at one side and rest of the term arrange in this bracket. So what you can write here? Half rho v square s by m, and this you can write Cy naught plus Cyp Pb divided by 2v. Okay, and plus Cyr Rb divided by 2v. Okay, and plus Cy delta A into delta A. Okay, So this you keep in a one bracket. Okay. Okay. This you keep in a one bracket. And what will be the rest of the term? This what I can write, you just consider this part plus I am taking, okay, this part plus I am writing here. Okay, so this part plus remaining part is what is half rho v s by m cy beta into beta plus cy delta r into delta r. Simple, right? First class. Okay, agree with me, right? So I am taking this plus sign and dot dot dot, that means I am writing plus this. Okay, now I can write this complete part as a d, disturbance in beta. So you can write d beta plus this, I can write half rho square s cy beta. I can write k1 beta into cy beta, k1 beta into beta and plus k2 beta into delta r. So what do you mean by this k1 beta? K1 beta will be half rho square s by m into cy beta. K2 beta is half rho v square s by m cy delta r. Simple, right? Now simple equation you have. Now what you can do, you can take a Laplace transform. So taking a Laplace transform, so what you will get, beta in s into beta of s into, you can in initial stage what you can do, you can this disturbance part you can neglect 0. Okay, it's your size, you may include also. Okay, so k1 beta into beta of s. Okay, and plus k2 beta into delta r of s. Okay, so what will be the beta divided by delta r of s will be the k2 what will be this, k2 beta divided by s minus k1 beta, right? So finally you obtain the transfer function, right? Okay, so deflect the delta, you will get the beta. Okay, now once you done with this, then that means your plant is ready. Okay, this is plant only, right? Now you should include the sensor model, delay model, actuator dynamics, everything. Okay, as we did for lateral and longitudinal autopilot design. So simple, the delay thing is same. What so far we have discussed. Using pod approximation, you can actually model delay or first order, second order transfer function. You can model the actuator dynamics. So same what we did in the longitudinal and lateral case, we did here as well. Now this beta into delta are ready. We are ready with this, right? You included the rudder, actuator dynamics, sensor model, delay. Okay. Now you may include what, rate and position limit also. First position limit, then rate limit. That means when you have a rudder, you cannot deflect beyond some certain limit, that means plus minus 30, let's say, and you cannot deflect with some rate, like you cannot deflect more than 80 degree per second or 30 degree per second, like that. So you have to put the physical limit, position and rate limit as well. Okay, now when I say delay, that means here I am taking the, it is taking a feedback. So when it's reaching to the controller, but from the sensor to the control block, it is taking time, right? So that kind of delay. Okay, and flight controller will take some time to perform the computation, that is some kind of delay. So 80 millisecond delay you can consider. So all the part is clear, right? So here you can see the washout filter is sitting there, though I will explain you in the next class, no problem. Okay, that's a different technique. So using this R also you can actually find out a rudder deflection in order to dam the yaw motion. Generally you will find in Boeing 747 aircraft or most of the commercial aircraft having yaw damper using this washout filter. Next class we will discuss in more, but we will now in today's class we will be focusing on the beta control. So this part is ready. So don't look at this part. Okay, this washout filter I will explain you later. Okay, now you have some kind of filter in order to remove the on-water signal. Use only PI controller. Okay, in order to control the beta. Okay, this part is ready. Beta you want to command 0. Take a feedback of beta. Apply the PI controller and control the beta. Okay, you have to tune this PI controller until you get the satisfactory performance. Okay, so this is how the rudder plays the very important role. Okay, now you can see I have neglected this d phi d beta equal to 0. If you include what you will see, you will have some kind of input disturbance here. This will be the d beta. This is the input disturbance. Okay, so that means when you are deflecting the rudder, there is already disturbance sitting on a rudder. Okay, that will create the problem. So you have to design the controller enough robust and enough gain margin, phase margin in order to handle this kind of disturbance. And disturbance can be the output also. Okay, as I explained already. Okay, so this is about the beta control loop. That means this is a very plays the very significant important role. So like for example, in this control you can see when you are taking a turn in order to attain the desired heading. So what we will do if you want to take a left turn, like in this direction, if you want to take a heading, okay, let's say this is a flying in a north direction. Okay, so if flying in the north direction and you want to take a 45-degree turn from the north, so what you will do, you will take a right turn. That means you have to perform a right roll. So you have to increase the lift in this wing and decrease the lift in this wing. So how will you achieve? By deflecting the aileron this and aileron up, down and up, then L plus delta L, L minus delta L, and you will roll. So due to centripetal force L sin phi, you will have a turning also, right? You will move, the aircraft will move in a circular path. Okay, so once the 45 degrees achieved, you can bring back to the roll to 0. But see, closely observe in this motion, when you do this, what will happen? More lift here, less lift here, it will try to take a yaw. So aircraft is nose is pointing in another direction, right? So aircraft will start moving another direction. That means it is moving laterally also or moving forward also, not desired, right? So that means every time you have to kill the side slip angle, right? So that means when you're taking this turn, so you have to deflect the rudder in this direction in order to make a coordinated turn. So every time you have to make beta 0 in a coordinated flight. So that is the importance of this control loop. Okay, and so for example, let's say if the aircraft is performing the landing and suddenly the wind is coming, so you have to handle the wind also. You have to correct the wind using the rudder. Okay, in order to have a smooth touchdown on a runway. You should not have a outside the runway, okay, while landing. Okay, so that is the importance of rudder. Rudder is a very powerful tool. And be remember, when you see during the takeoff of a single propeller engine, so it is if this propeller is rotating in a clockwise direction, so it will give the moment in a it will give a yaw in this direction, right? Okay, so what will happen? You have to deflect the rudder in this direction in order to align with the runway for a smooth takeoff, right? So that is the importance of rudder in order to counter the yaw moment as well. Okay, so that is why you will see when the pilot is sitting, so pilot uses the pedal, right? So if you deflect the right pedal, so that means the right rudder is deflected. But rudder is deflection in this direction. Okay, and you deflect the left one, so left will be deflected. And you can have a feel for this. You can put the elevator just vertically up, becomes the rudder. So that means when you pitching the elevator up, aircraft will try to up, right? Go up. Down, down. So similarly, rudder, if you deflect the in this direction, aircraft will go in this direction. Okay. If you deflect the rudder in this direction, it will go in this direction. Okay. So you can have a feel for the rudder in this way. Okay. So we'll meet in the next class. Thank you so much.